All right. So in order to explain what regression is, and we've gone through a lot of things related to correlation. Correlation is different from regression. Correlation is association between two variables. Regression is a causal association. So that is dealing with causal relationship. So regression is a statistical technique. It's not a mathematical technique. Where you look at a dependent variable being influenced by one dependent variable, one independent variable, and multiple independent variables. So as an example, if you have y, y is a function of, or it depends on several independent variables, x1, x2, x3, all the way up to as many of them as possible. Now, in this case, the variable that is being influenced is known as a dependent variable. That is a y. And all the other variables are known as independent variables. There are several names for them. Several names. For example, the dependent variable is also known as the outcome or response, or the regressand, whereas the independent variable is also called the predicted, regresses, and several other names for them. So today, what we want to look at is that there are different kinds of regression. There are different kinds of the causality relationship. You can have a dummy variable regression, ordinary least squares regression, GLS, generalized least squares regression, WLS, weighted least squares. There are several, depending on what you want to do with it. So let's try to get some few things. In a regression model, the standard regression model, what is it made of? So ladies and gentlemen, when you look at the standard regression model, you have a dependent variable, and this dependent variable is a function of a constant, and then a function of an independent variable, and then a function of another independent variable, on and on until you get the final thing known as the error term. I want you to know what a regression model is. This is a regression model. What is that? The regression model has 4 elements. Take note. It has 4 elements. The first one is the dependent variable, the one on the left-hand side. That is the one being influenced. That is the item being influenced. So for example, I'm going to give you examples though. So blood pressure level. The blood pressure is the main factor, which is now being influenced by the other factors. And what are the other factors? The other factors are known as the independent variables. So the x's are the independent variables. The x's here are the causal factors. We have several names for them, the x's. Explanatory variables, predictors, regressors. So these variables are those that influence. They influence the dependent variable. They influence the dependent variable. They affect the dependent variable. But the question is, by how much? By how much does each of the independent variable affect the dependent variable? By how much? Well, you will know how much each one affects the dependent variable using the beta parameters attached to it. Richard, your hand is up. That's your question. Richard.
Yes, Doc. Yes, Doc. Yeah, please, in the model, I am seeing X1 and then B1, X1, B2. So I was expecting to see, but I'm seeing B2, X3. I want to know. I mean, those are the independent variables.
What is your question?
Like I want to find out whether it. I mean, it doesn't make any difference. The X1 and then the B1, X1, B2, X3. The X3 is where the problem is. Because I was expecting to see X2, B2, X2, B3, X3, and.
Oh, okay. The way I wrote it.
Yes, please.
Okay. So it is B2, X2, just to be consistent.
Sure. Yeah.
Okay, I get it.
Okay. So thank you.
So the betas which are multiplying, the betas that are multiplying the x's, the betas are known as the beta parameters. What do? They tell you by how much the independent variable affects the dependent variable. I'm saying these things for you to get a picture. So the beta one here tells you by how much X1 affects Y. The beta 2 tells you by how much X2 affects Y. And what is interesting is that the essence of the regression model, the whole regression model, is to find those beta parameters. Now, as you can see, there's one particular beta which has no X attached to it, which means that that one is not one of the independent variables. It tells it's a mathematical analysis. Sometimes we call it the intercept, the constant. It has no economic interpretation. It has no sensible econometric interpretation. It is there to indicate that if all of the independent variables are not there, what is then affecting the dependent variable? So its use is not really pronounced, but it is only useful when you are doing prediction. When you want to predict what the dependent variable is, this beta naught becomes useful. But aside prediction, it has no economic interpretation. So the most important ones are the beta 1, the beta 2 that are multiplying the independent variable. Now, that leaves us with the last item. The last item on the modeling. And that last item is the error term, the last one. Now, the error term has got different ways. So I have used epsilon here. Sometimes you see, so you can have epsilon I. Sometimes you can have UI. Sometimes you can have EI. I just want you to know that it's the same thing. It is called the error term. It is probably the most important thing in the entire regression analysis. But then this error term has got several names. Who can tell me some of the other several names for the error term? And I want you to mention these other names because I'm going to use some of them for a certain reason. What are some of the other names for this? Okay, please, I want to know. Raise your hand and tell me. Be participatory. Tell me some of the. Justice, what are some of the other names?
Doc, idiosyncratic error.
Idiosyncratic error. Norbert, what are the other names for this error term?
Disturbance term.
Disturbance term. Fantastic. What are other names? Kofi?
White noise.
White noise. Normally used a lot in time series econometrics. What are other names? Kofi again. Oh, your hand was up. Isaac. Isaac.
Doc, please, the unmentioned independent variable.
All right, Isaac, I didn't hear you well. If you can type it there for me, because your voice.
Doc, please, I said the unmentioned independent variable.
All right. I don't know what that name is. Anyway, yes, Kofi again. Abdul Malik. Abdul Malik. Emmanuel Martinson. Unmute yourself and tell me. Your hands are up. Vincent.
It is residual. Yeah, it's residual. Can you hear me?
Who is talking?
It's Emmanuel Martinson.
Yeah, Emmanuel, go ahead.
Yes, it is residual.
The residual, fantastic. Very good.
Yes.
What is another name?
Abdul Malik here.
Yes, Abdul.
Reminder term.
What? That is not a good name for it. Please don't conjure names, oh. Don't conjure some names for me. Okay, I know all the names that are for this. Those of you who yes, Grace Asari.
Confounding term.
What? Grace, you are conjuring names. Please don't conjure names for me. Okay. When you say bonding term, what is bonding? Okay.
No, but I said confounding.
Confounding. Okay.
Yes, please, Doc.
All right. So unobserved heterogeneity. I see that when the residual, I see it typed there. Okay. Let me go to. Okay. So these are some of the names that you are observing. Those of you who didn't get it, write those names down because you see them differently. In some of your questions and assignments, I use them. Now, the word unobserved heterogeneity will come in a lot when we are dealing with panel data econometrics. Okay. But the most important thing now is what is it? What does it do? What is the purpose of this term? What does it do? The unobserved heterogeneity. Well, it is error. As the name, yes, Isaac. Isaac, ask your question. Isaac, you've been raising your hands anyhow. So anyway, it is the error term. The error term is, so here's the thing. When you tell me that these factors, the independent factors are affecting the dependent variable, at any point in time you tell me that, you are not able to tell me all the independent variables in the world that can affect the dependent variable. You are not able to tell me all the independent regressors that are able to explain or influence the dependent variable. So any other omitted variable is captured in this U term. So the U term captures variables that are, errors, misspecified errors, omitted variable biases, unobserved, factors that are invisible to you, but are actually behind the scenes that are also influenced. And I'll come to practical examples for you to get to this. So let's take a typical example. The wage, your salary. It is affected by education. It is affected by experience, by your position. Your position will determine your wage that you get, and also your ability. But of course, there are other factors that should have been accounted for. But ladies and gentlemen, yours is to tell me what could be the other factors that can affect the wage, but have not been captured here. And you see, who determines what is a relevant factor? Because they say you should tell me factors doesn't mean I should just mention any other factor that can affect wage. It must be relevant. So the unobserved factors must be relevant to unobserved factors. Because you can't go and say that church will affect the wage. So who can tell me some unobserved factor that can affect the wage? And again, I'm the only one here for now who will determine what is relevant and what is not relevant. Okay, because I've gone through it multiple times. So let me start with Richard. Richard, what other factor?
Yeah, hello, Prof. Doc, I think the nature and type of job can influence the wage.
Okay, so let me give you guys
the job.
Let me give you guys some help. Don't mention anything that is not easily quantifiable. Don't mention things like the environment. You get a point? Don't mention things that are not quantifiable. And again, whenever you're doing your research, the same thing. Don't mention things just like that. Don't mention things like quality, because the word quality is too broad, it's unquantifiable. So it is important that you go quantitative and you ask yourself whether this thing I'm going to mention is quantifiable. Okay, so on the basis of this, I will not take the example you are giving. Okay, so Richard, I will not take your example. Come back again with a relevant example. Let me go to Jewel.
Yes, Prof. Operational budget.
Operational budget is not relevant, because if you're going to give me my wage, it doesn't really depend on the operational budget. But there are several things that I rather can capture. Okay, let me go to Kofi Odrob watching. Kofi.
All right, Doc, I'd want to mention the factor of your dependency status. That's whether you have dependents or not.
So when your salary is being arranged, they look at whether you have dependency or not, and then that justifies your salary they give you.
No.
Yes, sometimes there are some special allowances that are given.
Don't use the word sometimes.
Others are not.
I'm asking you that they look at people's salary before family before they actually give them their salary. Is that what you're saying?
Well, since I'm not using the word sometimes, I also can't say it.
Well, that is why it is not relevant. Okay, so let's go on and get a relevant one. Okay. Vincent, tell me a relevant one. Vincent. Let me lower his hand. He's just not ready. Let me go to Osman. Give me a relevant factor.
Number of working hours.
Number of working hours is what actually determines the wage in the first place. Okay, that is the wage. Number of working hours is like you coming to the workplace. By virtue of the fact that you are coming to the workplace, it's even going to pay you. Okay, so that one is already embedded. Benessa J, give me a relevant factor.
Doc, can we talk about transportation? If not, distance to work.
Oh, you are trying to do two things. So if one is working. Okay. Anyway, so distance. Let's take distance. We call it location. Your location will determine your salary going up or down from another person.
Oh, please, no marks.
Okay, hold on. I determine anything. You don't determine marks here. I'm recorded, so I know it. So the point is that your location. So the people in London, they are paid more, okay, than the people outside London, because it costs more, okay, to actually be in London and then be working at the same time. Okay, so your location. will determine the work. And then that is what comes with the same transportation. Very good. Next person, Nyaba Clement. Give me another relevant factor. Clement, just mention your factor. Clement,
another relevant factor is the
Clement, type your factor. Your voice is not coming.
The nature of the work.
Okay.
Can you hear me, Doc?
Yeah, I got you. The nature of the work. Somebody mentioned it right now, and I said it's too broad. Don't mention that. And you are mentioning the same thing again. Let me go to Gilbert. Gilbert, give me one relevant factor.
Yes, please. Expectation. Salary expectation or wage expectation.
So you mean your salary expectation alone increases your salary?
It can determine.
That your salary expectation. Oh, you're talking about inflation.
No, not inflation. I mean expectation. Salary.
Yeah, when you say expectation, you are not speaking clearly. It's too broad. Your expectation of pregnancy, your expectation of delivery. But what is the expectation here? Okay. All right. Let me go to Farouk Adam. Come on, there are some easy, recognizable, relevant factors that you guys could have told me right now. Overtime is the right answer. I'm taking the word. Those who are not even talking. Okay. Overtime is a relevant factor. Richard Inti, that is a relevant factor. Overtime is a good one. All right, let's continue. Overtime. Okay. Overtime was mentioned. What other factors could you tell me? Those of you who have called, can you please lower your hand? It helps me to see those. Okay. Lower your hands for me. Lower your hands for me. Okay. And finally, let me go to Adongo. Adongo, tell me the relevant factor.
Minimum wage.
Minimum wage.
Yes, sir.
All right, okay. All right, minimum wage. Okay, you can lower your hand. Let me get another person who can give me another relevant factor. Abdul Malik. Your hand is still up, Abdul Malik.
We can take the risk. Yes, we can take risk exposure.
What you see, when you say these things, okay, it makes it very, very broad, but I'll buy it. Okay. So yes, risk. Okay, risk. Okay. For example, when you are in a mining sector, your salary will be higher than when you are in a different sector because of the risks associated with it. When you are in the airline, the risks might be higher than when you are not. So, all right, I'll buy that. And Richard.
Yes, Doc. I want to talk about the number of your subordinates that you supervise.
No, it doesn't. It doesn't, honestly, it doesn't. It doesn't. You can be in a company where you don't even have any subordinates and still your salary is still fantastic than when you have subordinates. Okay. So relevancy, over time, risk, location, okay. Sometimes even depending on the type of wage work that you are doing. So again, when you are doing your normal regression, try and make relevant factors. Okay. Let's take another one so that we don't delay. The blood pressure of a person is affected by the age, the weight, the stress, the pulse. But there are other factors that can affect blood pressure. Please, nobody should mention broken heart. Okay. I'm just mentioning some of the things that are irrelevant for you to start making them relevant here. Nobody should mention broken heart. So who can tell me a relevant factor that can also affect blood pressure? Let me start with Norbert. Relevant.
Your diet.
Diet is very good. Let me document that, okay? Yes, I agree with you. Your diet. Okay, what else? Can tell me the second factor. Second factor. And again, we'll determine that. Zelda.
Other diseases.
Other diseases, I'll buy that. Okay, other diseases, I'll buy that. Very good. Next, what other factors? Adoma.
Genetic predisposition.
Fantastic. Hereditary. Okay, hereditary. See, these ones, if you know them. If you don't know, you don't know. Okay. Now, all of you are mentioning relevant factor. I hope nobody spoils the relevancy. Ben is again.
Some situations in life.
All right.
Or let me.
It's okay. Don't worry. Don't justify it. Don't explain. You yourself, you got to know that it was not relevant. Now you are trying to make it relevant. So you don't worry. It's okay. Thank you very much.
No, please. I have
Don't
something
worry.
in mind.
See, that is why sometimes because you have the chance to unmute and mute yourself, okay? So now I'm going to allow me myself to unmute you. It's not relevant. Some situations in life, look at that. Some situations in life. Ima, how can somebody say some situations in life? Okay, without even mentioning situations, now the person is going to mention panic attack, is going to mention Russian-Ukraine war, is going to mention broken heart, is going to mention so many. There's some situations in life. That is not relevant. Sheila, tell me, what factor can affect? There's one particular factor that is not yet. Yeah, Sheila.
Lack of exercise.
Fantastic. That is the main thing. Okay, that is what I thought she was going to mention. The other one was going to mention. So exercise, okay, lack of exercise. I didn't say exercise. See, remember, we are talking about exercise or lack of exercise. So don't make it all negative. Okay. So you can say exercise, which means that if you are getting more exercise, your blood pressure will be lower. Or lack of exercise, which means that when you're getting more, when you are not getting exercise, your blood pressure will be higher. Okay. So we're not looking at positivity and negativity here. So when you look at diet here, we didn't talk about balanced diet. We just spoke about diet, and that's it. All right, so that is it. I'm not going to take more because I think that if I should start taking more, there will be irrelevant ones. So those of you whose hands are up, please type what you were going to say there, okay, for me to see whether they are relevant or they are irrelevant. Okay. Other than that, we are done with this. Let's go to another example. Okay, the unobserved factors is what we are looking at all this while. The unobserved factors. Okay. Somebody says sleep. How can you say that sleep causes or doesn't cause blood pressure? Okay. Everybody sleeps. Everybody. You get the point. That's why I didn't let you talk. I allowed you to type. Everybody sleeps. Children sleep or they don't sleep. So that doesn't determine blood pressure at all. There's no connection there. Okay. Somebody is also talking about work stresses, but already I typed, what do you call it? Okay, so stress. Some people think that stress leads to blood pressure. Okay, there is no relevant connection there. Lifestyle, another irrelevant factor. When you say lifestyle, it's too broad. It's too, very meaningless. Because exercise is part of lifestyle. So when you say, and somebody is talking about stress, when we have already mentioned stress here. Anyway, all right, thank you very much indeed. Let's go to the next factor. Okay, the next is the quantity demanded. Now, please listen before you actually think. So let me tell you why some people will do a regression analysis and it doesn't work well. They will do the regression, their results are not significant enough. Why? The reason is because they are including irrelevant factors. These irrelevant factors that some of you are including, that is what people do in a normal regression. And they are punished because there is something in the regression that you're going to learn that will punish you for including irrelevant factors in the work. Now let's take the third one, the quantity demanded of a commodity. The quantity demanded of a commodity is affected by the price of the commodity. We know that. The demand is affected by the income, okay, the income of the people. It is also affected by advertisement. Advertisement. Watch the words I'm using so that you don't repeat the same thing. It is affected by the complement price or the substitute, okay? The price of the substitute or the price of the complement. Of course, there are other factors which are inside the unobserved. So who's going to tell me? Please, nobody should mention taste and preferences. Okay. There are some factors that are questionable. So I normally want you not to mention it. Who can tell me a relevant factor that can affect the quantity? Somebody has typed it. When I said nobody should mention taste and preference, that's the first thing somebody has typed. Okay, raise your hand and tell me a relevant factor. Let me start with Zelda. Zelda, tell me a relevant factor that can affect me.
The location.
Location, very good. Location. Yes. Now, Adongo, tell me a relevant factor. Adongo, tell me a relevant factor. Yes, Adongo. Okay, he's not sure of his relevant factor. Justice. Oh, Justice. Tell me a relevant factor. Sheila, tell me.
Season.
Seasonality. Very good. Very good. Very good. I'll buy that. Okay. I'll buy seasonality. Seasonality is a relevant factor. Location. It's a relevant factor. Sheila.
Packaging.
Thank you. Thank you, Sheila. Okay. When we are talking about relevant, that is not really what comes in here. Okay. You see, when you look at words like packaging, marketing, all of these things are talking the same thing about taste and preferences. Okay. Yeah. That is not what causes demand. But the packaging is what affect demand. We are talking about generalized factors that affect demand. Farouk, give me a relevant factor, Farouk. Yes, Farouk.
Doc, can we say a religion? In
Yes.
the case of alcohol.
Yes, we can. Okay, we can say religion. In the case of alcohol. I like the point that has been written by Zelda. Zelda says price expectation. I'll buy that. That's a good thing. Price expectation. Okay. Price expectation can affect demand. That is good. Okay. Now, Isaac, when you say type of good, okay, again, I have mentioned income here. Okay, income. So the type of good and the income goes the same way. Complement or substitute. So again, the type of good, we've already captured these things. Please, those of you who have called, lower your hands. Emmanuel and Norbert, do you have another factor to mention?
Yeah, Doc. Sorry. The taste, the consumer taste.
Emmanuel, have you been in this class? Consumer taste. Norbert, I've indicated that nobody should include taste and preference. Then you come and say consumer taste. Norbert, you haven't been here. I think you haven't been paying attention enough. Okay, you haven't been paying attention. All right. So generally, these are the factors. Those of you whose hand are still up, please type what you think is relevant and let me see. Type it there, let me see. Type it what you think is relevant. Now, population is very good. Population is good. Abdul Basit. Uncertainties. Okay. When you say uncertainties, you are not really making. But again, you have to mention the factor instead of saying uncertainties, because everybody will mention the uncertainties. So if you want to say Ukraine, Russian-Ukraine war, mention that clearly. If you want to say COVID-19, mention that. But when you say geopolitics, again, that's too general. Okay. The weather is the same as the seasonality. Okay, so the one who has typed weather is the same as seasonality. So the prices, I told you don't mention quality, you're mentioning quality. Okay. Now, the prices of some products change according to season. So when Christmas is coming, the prices change. Okay. So that is why seasonality or weather. Weather, we are not talking about weather condition like hot or cold weather, sort of. All right. So that is it. So ladies and gentlemen, the ease of access is the same as the location. Okay. Look, don't mention anything because you've done economics. Elastic or otherwise. Master, elasticity has to do only with the price. And once price has been captured, it is the price elasticity of the demand or the income elasticity of the demand. So that point is not relevant. Okay, it's not relevant unless you're looking at in terms of the price, which is already captured here. So, ladies and gentlemen, these are some of the things when you are doing regression analysis. Your job is to be able to identify relevant and irrelevant factors should not be included. Okay, irrelevant factors should not be included at all, because the moment you keep on including irrelevant factors, the moment you do that, what happens is that you destroy the regression will punish you. The regression analysis itself is going to punish you because you have included what? Irrelevant factors. You have included irrelevant factors. All right. I'm trying to clean. Farouk, you have a question? Your hand is up. Do you have a question?
No, please.
Okay. I'm trying to clean. Let me just clear the annotations. Okay. All right. So I'm sure you are getting the picture here. If you're not getting the picture, ask a question. Adongo, your hand is up. Adongo, your hand is up. Is there a question? Yes.
Yes. You are stressing that we should avoid adding these irrelevant variables and a regression. So in that case, is it possible you further all conduct your the correlation to be able to identify those variables that have strong relation before you go with the regression? So those who don't have those variables that have no correlation, then those are left out.
Yes.
Is that possible?
Yes, but correlation is not the only thing you want to use. In fact, it's not really the main thing. You still have to conduct your correlation, but that is not what you are going to really use to determine relevance or irrelevance. There is something else that we do. We look at that will actually help you to determine that, look, this variable should not be included. It's irrelevant. Okay. And you're going to see that as we go through the regressional process. Okay. But of course, you have to do your correlation. Okay, that's why we did that earlier before we are coming to this. I don't know, you get a picture?
Yes, sir.
All right. Now, let's go look at the last one here. The last one is not a regression model. It's a regression equation. Now, if you look at the first one and the last one, they are the same thing. So if you look at the first one, and then you look at the last one, they are both wages. But there are two main differences between the first bulleted one, the regression model, and then the estimated equation. Who can tell me those two main differences between the estimated equation and then the regression model? Can tell me, Zaid, can you tell me the two main differences?
So the two main differences are the values of the coefficients are in the estimate, and the error goes to 0 in the estimate.
Excellent, excellent. So ladies and gentlemen, the difference between the regression model and the estimated equation is that the estimated equations are, the beta parameters are replaced with numerical coefficients. The beta parameters, okay, are replaced with numerical coefficients. So the beta 1, we now know the value of the beta 1 to be 0.85. Okay, you can see that here. The beta 2, we know the value to be 2.4. The beta 3, we know the value. Okay, so the values have been found, the coefficients, we call them the estimates. But before they are called estimators, okay, the betas are called estimators. And once you have their values, they are called estimates. So note the difference between estimators and estimates. The estimates are the numerical coefficients. And also the error term, which is the UI is gone. So if you look at the last one, there is no error term. Who can tell me why there is no error term in the estimated equation? Who can tell me? Be practical. Okay, I'm teaching you this course in a practical way, not in a very mathematical. When we come to the mathematical, some of you realize that, wow, okay. But in a practical way, why is the error term gone? Why is it gone? Kofi?
Okay, so we are trying to ascertain the effect of education, experience, and position on wage. By the time we finish estimating, we expect the impact of the error term to be 0 so that we can get the effect of the mean independent variables.
Good. So why do we expect the impact to be 0? That's my question.
So that it does not affect the impact of the other ones. It does not, I don't know the right term to use.
Yeah, why do you want it to be 0?
Because we don't need the error term factors. It's not what we are observing. So we don't want its coefficient.
That's the point. Okay. So the key point is what you said. We are not observing it. And because we are not observing it, we are not expecting their influence to be on the dependent variable. Okay. That's a very powerful point. We are not observing it. It is unobserved. So guys, when you look at the relationship between you and your spouse, okay, there are several factors that can affect the relationship. Some people will say money can affect the relationship. Okay. Somebody will say that communication. Somebody will say that, you know, what happens, you know, in times like, somebody will say that, you know, several things, but there are certain factors that are not observed. Now, those factors you can't think about, then you don't want them to influence your relationship. And so the error term, you would wish that the value of the error term is 0. When we come to the mathematics, and please take note of all of this, you will notice that the expected value of the error term will be 0. Okay, that would be one of the main mathematics of the error term. The expected value of the error term will be 0. In other words, the normality, okay, it will have a normality, a constant normality. It will have a 0 mean. That is what we mean by the error term will be 0. It will have a 0 mean so that its impact is not felt, so that the true impact are felt from the other variables. All right. So the essence of the regression is to find this error term factor. Justice, you have a question. Okay.
Doc, please, I want to find out what is the relationship between the error term and the B naught, because if the error term is going off and the B naught has no independent variable attached to it, so is there any relationship between the B naught and the error term?
Okay, so the B naught, I told you that it has no economic meaning. It has no economic interpretation. It is for cosmetic purposes. So that B naught is, you see, when people tell you that the B naught is just indicating are factors that affect the dependent variable when the independent factors are not there, it's not true. Because those factors must be there throughout, but they are not there. So the B naught is captured, okay? The B naught is captured inside the error term, if it is there at all. I want to repeat that. If it is there, so, but then in a normal correlation analysis, in a normal simple regression, cross-sectional regression, you will see that you bring the B naught, you bring the B naught, you bring the B naught. You see people bringing the B naught. Now they are bringing it, doesn't make it relevant. It is cosmetic. It is for beautification. It is not for relevancy. And that is why it's always good to deal with the panel data, because with the panel data, you don't even need the B naught. And so when you get to panel data, you will see that the B naught is not even part of the formulation. And so the B naught has no relevance. So to talk about what is the connection between the B naught and then the error term, if the B naught is important, it is inside the error term. It is encapsulated in the error term. That is the answer to that. That is if it is even relevant at all, if it is there at all. I hope you're clear. If you're not clear, you can raise your hand and then you can get it better. All right. So ladies and gentlemen, now that you get the picture here, now that you have seen some examples of how to formulate a regression model, and even you've seen examples of how to notice an estimated equation. Now that you've gotten all of that, let's get deeper. And I'm going to use a matrix to explain, because you see, when you are getting to the advanced level, it's not those many things that you are dealing with. Okay? In an advanced level, a regression, as you can see on your screen, the regression, the dependent variable is equal to the multiple independent variables. And now we have added beta k and xk. This k is indicated that there are several relevant independent variables. Okay, but because we can't write all of these, we sometimes use a matrix to represent them. Okay, now I want you to consider the y here like the different calculations of the quantity demanded of a product. So y1 would be the quantity demanded of product in shop 1. Y2 is the quantity demanded of product in shop 2. Y3, and then all the way up to yn, which is a quantity demanded of product in shop 40,000. So now you represent all of that with y. And then the beta naught, because it has no independent variables attached with it, has 1, 1, 1. And then the other independent variables are all captured here. In a matrix, the beta parameters are given their values in the fourth matrix there. And finally, your error term is captured here. Now, why do we use, I'll come back to this, why do we use matrix in a regression? Because this is an area a lot of people don't like. But you use the matrix for a certain reason, because it helps you to make bigger things smaller. The matrix is like a model. You know, when you have an aeroplane, the aeroplane is big. You cannot actually fidget with it because it's real. And so if you want to actually fidget with it, you will have to make a model of the aeroplane in a small part that can be in your hand, or you can make a model on the computer. So that model is a representation of reality. What is real? The matrix is a model, is a representation of reality. Okay. And of course, whenever you are talking about matrix, you need to know the matrix, whether it is a row matrix, a column matrix, a row column, and all of that. And so for the regression, because it is a dependent variable, it's an n/1 matrix. It's an n/1. The independent variables are n/k+1 matrix. The beta parameters are k+1/1 matrix, and then the error term is an n/1 matrix, just like the dependent variable. Okay. Now, I'm not going to go deeper into this, but I want you to know the basics. Now, given these matrices, we can now represent all of them by y equals x beta plus u. Now, I want you to see the y as the bucket of all the dependent variables. And I want you to see the x as a bucket of all the independent variables. So all the independent variables, x1, x2, x3, xk, all of them are captured into the x. And then I want you to see the beta parameter as a bucket of all the beta parameters, beta 1, beta 2, beta 3. And all that. So this is an easy model that you can manipulate and make sense of. That's a matrix. Now, I want you to pay attention here as I walk you through the properties of the OLS estimators. Now, what do I mean by the estimators? The estimators here are the betas. Okay, so the beta parameters here. The goal of the regression is to find the impact of the independent variable on the dependent variable. And these impacts are reflected in the beta parameters. These beta parameters, beta 1, beta 2, beta k, all of that, these are called estimators. And there are certain characteristics of them that you got to know. In fact, they make up what is known as the assumptions of regression. The method for estimating a regression model, okay, the old phases of method, there are several methods, but the standardized classical method is known as ordinary least squares, OLS. The ordinary least squares regression is a method for estimating the parameters, okay, the following parameters of the regression. Now, what are the properties or the characteristics or the assumptions underlining this OLS? What are the properties of the estimators and all the assumptions underlining the approach? Now, when I say assumptions are certain things that must be there for certain things to work. So please take note. What are assumptions? Assumptions are certain things that must be there for certain things to work. So the moment I say the business school has started operating, I've already assumed that what is happening? The moment I say that the business school is operating, once I say that the business school has reopened, I've assumed that what is happening? What is already there? That's what I mean by assumption. I've assumed that what is already there. You can tell me, or you can type it. Okay. The moment you say that the business school is operating, then you have assumed that what is already there, what is already happening, what is already happening. Yeah, Farouk.
Lectures are going on. That means that there are lecturers and there are students on campus.
Good. So you have already assumed that lecturers are there, students are there, the building is there, the markets are there. You know, so the moment you say that you are doing a regression, then you've assumed that what is there, and that's what we are going to look at. Okay, what are the characteristics of the beta parameters? I want you to pay attention here because this is the most important thing. You will need this in everywhere else that you are doing. Okay, sometimes when you're even writing theses, you have to make those assumptions explicit. The first assumption or the first property of the estimators is what I said earlier, that the expected value of the error term, of course, given the independent variable, should be 0. Now, what it means is that the error, Kofi Gogovi indicated that the errors are not needed. And so because the errors are not needed, when you are doing the regression, you expect these errors to be what? To be 0. You're expecting the errors to be 0 because they are not needed. Okay? Because they are not needed, you want them to be 0. So one of the assumptions, one of the properties of the estimator is that we want the error to be 0. Now, this is known as weak heterogeneity, and I'll come and explain it later. Okay? Because when you were assuming that the error is 0, you were assuming that the error is 0 given the dependent variable. So it wasn't like the dependent variable were changing. They were fixed, giving them before you now say that the error term is 0. Now, there's another one known as strict exogeneity. Strict exogeneity happens in the panel data. What we are looking at here is the cross-sectional. I'm sure by now you all know the difference between the two, the cross-sectional data. So in the cross-sectional data, we are talking about the weak exogeneity. In the panel data, we are talking about the strict exogeneity. Because in a panel data, when you are assuming that the error is 0, you are assuming that the error is 0, given that, not just given that the independent variables are fixed, but also the independent variables are fixed over time. This is critical. They are not just fixed, because in a panel data, you have time element. So you're assuming that the independent variables are fixed over time. When we come to panel, you'll get that deeply, but I just want to flag that. So the first assumption of these estimators is known as zero mean, the zero mean assumption. That's the first one. If you don't understand, okay. The second assumption is known as homoscedasticity. Homoscedasticity. Now, again, these things might be quite overwhelming, so I'll try and make it a bit simpler. Now, I want you to, the last time I showed you guys when the pattern, do you remember the pattern that I showed you? Okay, let me just draw some of them here for you to get a picture. There are patterns in the errors. Now remember, this is homoscedasticity of the error. Take note of the error. So you can have a situation where you have the error term and then the independent variables. Homogeneity is when there is a constant pattern, okay? A constant pattern of the errors. So what it means is that the variance, the disparity between each observational error is constant over time. But then, and of course, this is an example of what I've drawn, but when you have a situation where you have a particular variance, and that variance is scattered, and there's no proper, there's no proper disparity or variability, then the constancy of the error is said to be heteroscedastic. So homoscedastic error is when the variability of the error observations are constant. They are constant. In other words, there's a pattern that you can look at. Now, how do you write that mathematically? You write that mathematically by saying that the variance of the error term given the independent variables is constant. That is, it's equal to sigma squared. Okay. If it is equal to sigma squared, then it means that it's constant. Now, the pure mathematical way of writing the first one and the second one is that the error, you see now I'm using epsilon. Okay, sometimes I'll use mu, a ui, sometimes I'll use epsilon. So epsilon is an independent and identically distributed, term. Now IID is an independent and identically distributed term. So it means that when you were collecting the data, it was a random analysis that you did. This error term is normally distributed, that is the n here, is normally distributed with a zero mean and a constant variance. So this whole thing puts everything together for the first and the second bullet. The error term is normally distributed with a zero mean, that is the mean, the average of the errors is 0, or the expected value of the error is 0, and a constant variance. A sigma square with an identity matrix that you see here indicates a constant variance. Welcome to the world of regression statistics. Okay, so that is the two properties. Okay, those are the two properties of regression that you want to take note of. That is not all. The next assumption of a regression, which again, when you look at it, all of these assumptions are about the errors. Look at them. It's all about the error. It's all about the error. Okay, it's all about the error. Okay. So the next one is no autocorrelation or no serial correlation. When we are dealing with the panel data, we talk a lot about no serial correlation. Now, what is serial correlation? Before you tell me that there is no serial correlation. Now, remember, the serial correlation has to do with the errors. Now, the errors, you can have different errors. And why can you have a different error? You can have a different error because remember, the y's can be different. The y's, they can be different. You remember when I was showing you the matrix, the y's were different. Let me just go back and show you. Okay. Look at it here. So you have y1, and then you have U1. Okay, so you have a particular error, which is U1, and you have another particular error, which is U2. Now, they can be related. One can depend on another, and you don't want them to depend on each other. So the next assumption says that there should be no dependency, or there should be independency of the errors. This is sometimes known as the orthogonality. In other words, the errors must be orthogonal. They must not be serially correlated. In other words, the relationship between error U1 and error U2 must be zero. There mustn't be any connection, any correlation between them. And another mathematical way of writing that is saying that the covariance of UI and UJ should be equal to zero, where the I is not the same as the J. They are two different errors. Now, this is very pronounced. This is very big issue in time series econometrics and panel data econometrics. But in a cross-sectional econometrics, it's not a big deal. But the key point is that, see, there mustn't be any relationship. Do you guys remember multicollinearity? Do you guys remember when I explained multicollinearity in class? Who can remember that and explain that to me? Do you guys remember who can remember multicollinearity? I think somebody asked the question, and I use your salary is dependent. Fantastic, I got some answers there. Yeah, Justice, unmute yourself and then tell me. Okay. Multicollinearity. Multicollinearity. Who remembers that?
Hello, Doc.
Yes. Yes, Isaac.
Doc, please, it means that we have independent variables relating to each other. That is correlating among themselves instead of impacted on the dependent variable.
All right, thank you. Thank you. I appreciate that a lot. Okay, I appreciate that. What do you want to add? Because his network wasn't too welcome. Boyson, is there something you can add to that? Boyson, just unmute yourself. Yes. Yes, Boyson, go ahead. All right, let me go to Zelda.
Look, when two independent variables are highly correlated, that it becomes difficult to disentangle the partial effect on the dependent variable.
Fantastic. Now, when what she said was when what are highly correlated, okay? She didn't say when the errors are highly correlated. No, she said when the independent variable. So you have xi and then xj. You see the word? Xi and xj are highly correlated. Then we have an issue of multicollinearity. Now here we are not talking about xi and xj. What are we talking about? Ui and then uj. So when the errors are highly correlated, then we have an issue of autocorrelation or serial correlation. And one of the assumptions of regression is that there mustn't be that. Kill the principle of serial and autocorrelation there. When you don't solve that, and all of these things that I'm showing you, we're going to show how they happen. We're going to solve them one by one. This is the whole essence of the regression. We're going to show how they happen and then correct each one of them. Okay, so the first three you've seen so far are about the errors. Now let's look at the other ones. Okay, the other ones. Now the other ones are a little bit tricky as we move further with those ones. Okay, they're not that simple like the one we just looked at. The first one, which is still a continuation of the classical linear regression model, okay, assumptions of the Gauss-Markov model. Now, all of these terminologies simply means that there are several names of calling this OLS regression assumptions. OLS, classical linear regression model, Gauss, Markov, okay, bell-shaped assumption. All of these things are the same thing. Because regression is a mean analysis. Regression is an average analysis. Okay. That is why you draw a regression line. You shall look at that. So the next assumption says zero covariance, zero independence. Now, please note the previous one and then compare it with this. The previous one is the covariance between two errors should be zero. The covariance. The two errors must be uncorrelated. The two errors must be uncorrelated. Now, this second one, zero covariance, is talking about zero covariance between the error and the dependent variable. So you see, the covariance between the error and the dependent variable must be zero. So it's not like the covariance between two errors must be zero. No, it's not like there must be zero serial correlation between two errors. But even between the error and the independent variable, there shouldn't be any correlation. Now, when there is a correlation between the error and the independent variable, what's the name for that? Who can tell me? I'm just taking you further. When there is a correlation between the error term and the regressor, then we have an issue of what? Justice?
Autocorrelation.
Yeah, but then when there is an issue between the error, remember, it's between the error, and the independent variable. The autocorrelation is between two errors, but the error and the independent variable. Okay. This is deep. This is deep. When you know, you know. Yes, Francis.
Doc, is it endogeneity?
That is the problem of endogeneity. Okay. Now we have a problem known as endogeneity. I'll come back to this point because it's more pronounced in a panel data econometrics. Okay. So now you are dealing with the problem of endogeneity. And when you hear of endogeneity, of course, there are three things that cause endogeneity to happen. And one of them is this, a zero covariance. And please note, it's between the errors and then the independent variable. Now, the next assumption is that before you can do a regression, the parameters, the estimators, the beta, they should be linear. And I'm talking about sample regression. And I'm talking about basic regression, not nonlinear regression. So the regression says that the relationship must be a linear relationship. There must be a linear relationship between Y and X. So again, this one is not about you again. Okay, the relationship between Y, okay, and then X, okay, the relationship must be linear. Please note, when we say linear, we are talking about a line. Linear is not curvilinear, it's not quadratic, it's a line. So watch it. If you have X here and you have Y there, the relationship between X and Y here, as I'm doing it, is linear. If you have X here and you have Y there, the relationship between X and Y, just watch how that is linear. Okay, so linear doesn't mean that it's always downward sloping. It can be upward sloping, it can be horizontal, it can be vertical, it can be downward, but the relationship is what? Linear. And I want you to get that point. Okay, it's still linear. So you got to make an assumption that the relationship is a linear relationship. Now, the moment you gravitate towards nonlinear regressions, a nonlinear relationship, it's only the nonlinear relationship can only happen among the regressors, but not among the parameters. So the relationship, okay, between the individual regressors, that is the independent variable, can be nonlinear. But between the parameters, the beta parameters, the betas, because there's a beta that defines, you know, that's the slope of each regressor. That one must be linear. Okay. All right. But please note, when you have linear relationship, it doesn't mean that you cannot include logarithms. You can include logarithms. And later on, you come and understand why we have to include logs. Okay, so the model can have logarithms. Okay, so you can have the log of K. You can also include squares. So you can have K squared. Okay, you can have the log of K. Okay, but of course you don't just introduce them. Okay? And then you can also interact some variables. You can interact two independent variables, or even an independent variable and a dummy variable. So you can have x1 multiplying x2 as another column variable. And you can have a dummy variable like we have in our work. Okay, income and then occupation. Income is a numerical variable. Occupation is a dummy variable. You can multiply the two and get a new variable. Why do we do interaction variables? Why do we do moderating variables? Why do we square some of the variables? Why do we log some of the variables? We will look at all of this in a panel detecting matrix. Okay, so the variables, you can do a lot, but then the parameters must be linear. That is what we are saying. The parameters, the relationship between the parameters, they've got to be linear. They've got to be linear. So that is another assumption of the classical linear regression. Okay. Well, when you hear the word OLS, ordinary least square is linear. Okay, that one. Now, regarding the multicollinearity, now you can see that one is there. There must be no perfect multicollinearity. Please note, we didn't say there must be no multicollinearity. Now, we said there must be no perfect multicollinearity. So it means that you can have multicollinearity. You can even live with it. We'll look at that. But there mustn't be perfect multicollinearity. Like two people, two variables, they are doing the same thing perfectly, and you want to keep both of them in the model. It's not good. Where you have experience, okay? Suppose you have experience, and then experience is doing the same thing as education. The same thing, they are perfectly correlated. The correlation between the two is 1. And you want to include both of them in the model. No, we need exogeneity. We need exogeneity. The word exogeneity, not endogeneity, but exogeneity means that the independent variables are not dependent on each other. That is exogeneity. They are separate on their own. There is no dependency. Exogeneity is independence of the independent variables. Take note. These are critical, terminologies that you want. Okay. So that is what we discussed earlier. So whereas multicollinearity has to do with the independent variables, autocorrelation has to do with the errors. Whereas multicollinearity has to do with the independent variables, autocorrelation has to do with the errors. Take note of that. Take critical note of that point. Okay. And then another assumption, another quite basic assumption is that there must be no specification bias. In other words, the model you are going to write must be correctly specified. So the way some of you were mentioning some model. So when you have a model and you're going to get some of this, we do different modeling. Okay, weighted least square, generalized least square, feasible generalized least square, okay, feasible GLS, and several other things. When you are modeling, suppose you are modeling a quadratic function, and you say that Q is a function of capital and then labor, okay, given technology, okay, or something else. When you are modeling the whole analysis, and you say that capital is to the power half, labor is to the power half, okay, this model is a kind of a quadratic model. It's a kind of it's a Douglas production function model. But you can take the log of this model and then go ahead and then simplify it. Now, when you mistakenly specify the model, so let's say that the model is supposed to have it to the power half, and you make it like, half of to the power half. When you model the model in a different way, we don't need maybe a technology. Technology doesn't need a cube. And then you bring a cube to it. You have misspecified a model. Because anytime you are doing the model, the way you write a model is critical. And one of the problems, one of the challenges of regression is that if you have a wrongly specified model, that will affect your results. And so your interpretation will be wrong. And that is why the rule says that there must be no specification bias. Okay, there must be no specification bias. So guys, you are going to do some modeling. So take note of all of these assumptions. Now, let me quickly explain. Any question, by the way? Any question before I continue? Any questions so far? Any questions so far? Any question? All right. So there are some few things I want you to note before we come to the practicalities. One, sometimes in a regression, especially in panel models, you have to take the log of some of the regressors. I've said that. Okay. And why do you do that? You take the log in order to impose a constant percentage effect. What do we mean? You take the log of some variables because you believe that inflation would have affected those variables. For example, price. So when you're doing some variables and then you have one of the columns to be GDP. GDP is affected by inflation. And so you can take the log of that. Price is affected by inflation. Income is affected by inflation. So you can take the log. Interest rate is affected by inflation. Exchange rate is affected by inflation. Bank deposit is affected by inflation. So there are some variables that you know that these variables are affected by inflation. Then you can impose a log on those variables in order to remove the nominal effect and get a real impact, okay, the real value of those variables. So to do that, you log the variables. So when you look at some of the regression papers, they will be taking a lot of logarithm. But please, that is not to say that you have to take log all the time. It has to make theoretical sense before you do that. We'll look at some examples, a practical example of that. Okay. Some variables, you have to take their squares. Their squares. When you take a square of a variable, well, a variable, say, let's talk about a variable that is called size. Size is sometimes measured by the total asset of a company. Okay, the total asset of a company. Now the size grows. The impact of size on a particular variable it's higher. So as you grow the size, as the size of a company grows, the idea is that it affects the profit margin of the company. But then there is a rule also that if the variable, if the company grows too much, there could be a problem. There are so many theories on mega measures, the negative impact of mega measures. And so because of that, size itself is good, but as you grow further, size will negatively affect. It's not all the time, but then that is a theory. Okay, because there will be problems on monitoring. You know, when the company becomes so large, for example, you have a very large army, you can't even control, you can't even have, you know, when you look at the ministries, there's a very large number of people there. The size is so big. So people go to the ministries, they go and work. You don't even know whether the person came to work or didn't come to work. Some people will just go there. You cannot calculate their output, they bring it to the company because the company is so large. That is a negative impact of size. There is no monitoring. It kills coordination, it kills monitoring, and people even check. Some will be lazing about. Somebody will say that I don't want to do it, this guy would do it. And so there's a checking. So you can capture size. So in this case, you now take a square of size to indicate that that variable can rise, get to a point and fall. You see, when a variable is going this way, okay, that is constancy. But when it goes this way, it gets to a point, you think it's a fall, its impact on the dependent variable will reduce, then that variable must be squared. So there are certain variables you got to take their squares. And that will handle the non-linearity. Okay? Because what I've just drawn here is a non-linear structure. And some variables, you have to interact them because you believe that when I'm able to interact capital structure with corporate governance, I will be able to see a better impact than just looking at the impact of capital structure on performance. So you believe that capital structure and corporate governance must be interacted. So if capital structure is X1 and then corporate governance is X3, you will create a new variable, which is X1, X3, by multiplying them and then running that in the regression model. You can do that. And that is an example of interaction. But then what about mediation? Mediation deals with causal sequence. It's different from interaction among three variables. Okay. So let's take a variable like X, M, and Y. So a variable X will affect M. Okay, and then a variable M will affect what? Y. So you can use the variable M to mediate between X and Y. Okay, that is sequential, but interaction means that X affects Y. Okay, so X affecting Y directly. That is interaction. Okay, so X is affecting Y directly, but you are interacting X with something else, like I just did with this example. Okay. But with mediation, you are looking at X is affecting M before M affects Y. You are not interacting. So that is what it is. Please, I saw a hand. If you have a question, raise it so that you can ask your question. Okay. If you have a question, raise it. You can unmute yourself and ask. Yes, Richmond.
Hello, Doc. Yes. So I just wanted to understand the interaction and the mediation. So it means that for the mediation, you have to interact the X and M before you can, before it can mediate the Y. That's what I want to understand. I'm a little confused there.
You don't need to interact the X and Y. Okay. So mediation, okay, is not generally done even in regression properly. So you use structural equations modeling to do mediation properly. So you can do it in a regression, but you have to kind of do two-stage analysis. So you do something known as X variable affecting M. So M becomes a dependent variable. So the M is a dependent variable, which is being affected by X1, X2, X3, X4. Now you have the M, but that M is not the only variable you have. Now you are going to have Y being affected by M1, M2, M3. So what it means that X1 affects M1, X2 affects M2, X3 affects M3. Then once you have these, these things which were dependent variables in the original model become independent variables. Then you look at their impact on Y. That is mediation. But interaction, you are just looking at X. Let me use a different color. You're just looking at X1 affecting Y. You're looking at X2 affecting Y directly. And in that process, watch it. In the process, you can multiply X1 and then X2 together to create a new variable. Now, that is not mediation. Because mediation is when you are saying that something is affecting something before that second something affects the third something. But interaction is where you are saying that this and this together. So you're not even looking at effect. You're looking at multiplication, the product of the two variables. Does that make sense? Yeah. When we come to the practicalities, then you can understand. Yes, Francis.
So if I get you clear, so mediation is like, say you're using M as an instrument for X.
That's it.
You now use X to.
Exactly.
Okay. All right.
Yes, mediation, you're using it as an instrument. Okay. You're using it as an instrument. So later on, that is latent and it's affecting this one.
All right, thanks.
So, but like I said, you don't do much of mediation except in some rare situations. Okay, you don't do much of where you call it mediation. You know, like we just use. Okay, but if you are doing it properly, you call it an instrumental variable. But you don't really call it mediation. But in a proper structural equations modeling, that one you see mediation because there are a lot of latent variables. So most of you will be doing interactions more than mediation. That's the key point. Most of you will be doing interactions more than mediation. All right. So take note of all of these factors, because when I give you a model, when I give you a model, and I'll do an example first. When I give you a model, I will expect you to note which ones you should take the log. That's what I will expect you in an exam to do. Which of these variables, I'll give you the data set. Which ones, using your knowledge, which ones are you going to take their logs? Which ones are you going to square them? Which ones are you going to interact them? These three things. And so you got to know. You got to know yourself. And that is why I'm taking my time to explain all of this. All right. So now, how do you estimate the estimator? How do you estimate the regression? Well, I've already said the estimator is a kind of a rule, a recipe. Okay. Now, you use the estimator to get the estimate. To get the beta parameter, there are several ways of dealing with it. One of the commonest ways is known as the ordinary least squares. It is sometimes attributable to Adrien Marie Legendre in 1805. So OLS is one means of estimating the beta parameter. Maximum likelihood estimation is another means of estimating the beta parameter. Now, you guys, you do maximum likelihood estimation when we come to limited dependent variable regression. You do that. GLS, okay, is another means of estimating. That came later in 1935. Then you have feasible GLS, which is also sometimes called the weighted least squares. These are all several ways of estimating the beta parameter. You see, guys, what it means is that this beta parameter, how you estimate it is important. So different models have been proposed in the estimating procedure. Let me show you in a matrix form. Yes, Kofi.
Oh, please let me take you back again. You said we use the MLE for what?
We use it a lot for limited dependent variable regression, like when you're doing truncated regression, probit regression, logit, regressions, tobit, censored regressions. Okay? These are all limited dependent variable regression.
Okay.
And you need a maximum likelihood estimations to be able to do all of this.
Okay.
Now,
thanks.
How do you find the beta parameter? Guys, I will show you how to find the beta parameter using even Excel, using R. But I want you to understand what is really happening behind the scenes. Because some of you want the easy way out, easy peasy. So I want you to understand the mathematics, the statistics of what is happening. So follow me. Follow me. And we're going to use a matrix for this. Some of you will be slightly confused if you don't follow. So please follow. So here you have y being equal to x beta plus the error term. Please note that this error term, I could have used ui for it. I'm going a bit slowly. Okay. Now, I'm going to do something to this formulation. And when I do something to that formulation, it doesn't hurt anything. It's because of what I want to achieve. And before I do something to that formulation, I want to share something with you. If you have 2x equal to 6y, and this is an equation, and let's say 6y plus 4, okay? And guys, I said that I'm going to multiply the 2x by w. So I have w into bracket 2x. And because they are equal, I'm also going to multiply this one, 6y plus 4. I have a question. Have I changed this model? Have I changed it? What I've just done. Okay. If you look at the first one, oh, if you look at the first one, which is this, and you look at the second one, have I changed the model? And please don't answer yes or no, because I ask you why. So those of you who are going to answer yes or no, I ask you why. Okay. Have I changed the model? Emmanuel?
No, you haven't.
Why?
And the reason is that the effect on the left-hand side or right-hand side is going to be constant.
Good. So because if I divide both sides by W, I'll cancel it and I'll get back my own. So I can manipulate a model with the intention of achieving something. I want to repeat that. You can manipulate a model with the intention of achieving something without changing the model. You have not changed the model. Keep that in mind. That point is a very critical point. Before some of you, actually ask me what is happening, what are you doing? So now let's try to do something to this model that you guys can see. I'm going to multiply through this model with a matrix. Okay, so I'm multiplying the first one here with a matrix X prime. X prime, the transpose of a matrix, X prime Y, and I'll do the same thing with the others, X prime X beta, and I'll do the same thing with this, X prime epsilon. I've done that. I have not changed the model. I've only introduced something. If I decide to divide all by X prime, I get back my original. What is X? X is a matrix. Okay, in case you guys have forgotten, X is a matrix made up of several things. Okay, let me just show you an example. X is a matrix like this, made up of several things. X1, 1, X2, 1, X3, 1, and each of them is a whole matrix. This X is a whole matrix. And X prime is just turning it. Okay, so if it was a horizontal, I'm turning it into vertical. If it is a vertical, I'm turning it into horizontal. I'm letting the rows shift to become columns and the columns shift to become rows. That's a matrix. Okay, I can do something to this model again. Given this model, I can now multiply through again by X prime X to the power -1. So look at the first one, X prime Y. I multiply this X prime Y by X prime X to the power -1. And that means that this second one too, I'll multiply it by X prime X to the power -1. Then this one, I'll multiply it by X prime X to the power -1. But something will happen with the last one. The last one. It is X prime X. Let me just write it here. And again, normally, for your level, I should have even let you go and do this. Okay. So this last one is X prime epsilon. I'll multiply that. Okay. I multiply that with X prime X to the power -1. What happens? Well, this whole thing will break down. Why? To 0. Who can tell me why? This whole thing that you are seeing here, okay, will break down. Even though you don't sense it, it will break down. And who can tell me why? And again, you are going to use some of the assumptions of regression to break it down to 0. Now, the expected value of X prime is X prime. The expected value of X is a matrix, is X. The expected value of Y is Y. The expected value of the error term here is what? You can tell me. What is the expected value of this error term? What is the expected value of this error term? What is the expected value? Boyson. Boyson. Boyson, go ahead. You are unmuted, so go ahead. Boyson, I don't hear you. I don't know whether you talk or you don't. Yes, Emmanuel.
We said the expected value of the error term is 0.
Okay, so if the expected value of the error term is 0, and again, you guys should know this, we have that already. Okay? Expected value of the error term, okay, is 0. If it is 0, that 0 will multiply all of this, and everything here becomes 0. That's what you see there. So it doesn't change. Okay, it doesn't change. It doesn't change. The only thing that is gone is that error term is gone. Now, on the basis of this, you can do something to what is left. You can do something to what is left. Now, watch something. Guys, what is, let me just write it here. What is 2 raised to the power, if you have x raised to the power -2, okay? And then you have x raised to the power 4. What do you normally do with it? You know the x is the index and then the power is the exponent. When you multiply these two things, what do you get? When you multiply these two things that you see that I've done here, okay, in your normal exponent and index calculations you did undergrad. Richard, what do you get?
So you get S squared.
Yeah, but how do you get it? How do you get? Show us.
So you because the bases are the same, you add the indices. So it will be -2 plus 4.
So you guys, you have -2 plus 4, which is what?
2.
Which is 4 minus 2, which is 2. I'm saying these things step by step, which I shouldn't, because somebody is probably thinking I'm speaking Hebrew. So I need to just go step by step here. So now that principle is what we are going to use here. So now you have this x prime, and look at this one here. Okay. Look at that. You have this x prime x to the power -1. And then you have another one here, which is x prime x to the power 1. You don't see it, but it's to the power 1. Okay, so that will mean that, okay, watch it carefully. That will mean that you are going to have x prime x to the power 0, because -1 plus 1 will give you what? 0. And any number raised to the power 0 is what? Is what? Just shout the answer for me. Yeah, mention the answer. Emmanuel, any number raised to the power 0 is what?
1.
Is 1.
1.
So now you have 1 for the right-hand side. 1 is multiplying beta. And so you are left with what? Beta. That is how come the right-hand side here is beta, but the left-hand side is still there. Lower your hands, please. The left-hand side is still there. And so on the basis of that, you can now conclude that this beta is equal to x prime x to the power -1, x prime y. This is a simple thing. This is what the software is using. So when you actually ask the software to calculate the beta parameters for you, the software has this formula in its memory, and it is calculating each beta for you using this principle. Remember, these are matrices. They are a whole chunk of data set. It's a whole data frame, but the software will work out which ones are the independent variables, which ones are the dependent variables, which you have given it. It will commandeer and use it to create the beta parameter. This is how the beta parameters are estimated. This is how you find the beta parameters. I saw somebody's hand. Isaac, do you have a question? Isaac, your hand is up. Isaac, Abo. All right. So the OLS parameter, the OLS regression, it uses this simple approach I just showed you. Now, in a simple language, what you are seeing down here is pure statistical, analysis. But again, that's what we've gone through. So to be able to get this, you have to know what your X is. You have to know what your X is, what your Y is. That's all you need to know. As for taking the inverse and then taking the transpose of that, you see it's just a matter of working out this. And once you do that, the beta. So this is what is happening behind the scenes. Anytime you are finding, now this beta is the mean. Remember, regression is finding the mean. You draw a line through the entire data set. That line is a line of best fit. The word best fit means average. And anytime in a central tendency, you have the mean, the median, the mode. These are measures of central tendency. Okay. Anytime you have that, you must have a dispersion from the mean. You must have a deviation from the center. And so you must have the variance. And so the next thing regression does is to help you to find the variance. And to be able to find the variance, you need to calculate the variance covariance matrix. And this is a variance covariance matrix, because from the variance covariance matrix, you'll be able to know the variance and you'll be able to know the covariance. Now, sometimes when you're calculating these things, people will just, okay. So the way I calculated the previous one for you, I'm not expecting you to automatically be able to understand the second one. I'm not expecting fully. Some of you will get it, but not all of you. If you don't get it, don't worry, go through it. It's a very systematic thing. So we just want to prove that this beta cap, the variance of beta cap, the beta cap here is the estimated value. What's this? Idrisu, ask your question. Idrisu, your hand is up. Ask your question. Idrisu Mohammed. All right. So the variance of the beta, remember we calculated the expected value of the beta is beta cap. We just calculated that, the expected value, the mean. We've gotten the mean, and that was the previous one. We just got the mean here. This is the mean. Okay, that's the expected value of beta. The expected value of beta is beta cap. Okay. Expected value of beta is beta cap. Now, how do you find the variance? The variance is equal to sigma, the variance is equal to sigma square x prime x negative 1. Sigma square x prime x negative 1. But how do you arrive at that? How do you arrive at this sigma square x prime x negative 1? Well, it's a very simple thing. First, understand this few things. The variance of beta cap is expected value of, look at what is here. It is this whole term prime and the same term without prime. The prime is like to the apostrophe. So the beta cap minus beta, what is the difference between beta cap and then the beta? The beta is the true value. Okay, remember the independent variables are trying to affect the dependent variable. But what is the true value of the impact of the independent variable? What is the true value? That is a beta. But that true value is unobserved, because in the real population of the world, that true value is unseen. And so what you do is I need to collect data and you estimate. That's why the thing is called an estimate. When something is an estimate, it's an estimate of the estimator. So the beta is a true value. This beta is a true value. And this beta cap with a hat on it is the estimate of the true value. And that is what we did in the previous slide. So the expected value of this with a prime and the same thing without a prime is the variance. We are going to use a certain principle to arrive at the variance covariance matrix. So recall that the beta cap, the estimated beta, is x prime x to the power negative 1 x prime y. We know this already. We just found that. Okay. Now, if we substitute the value of the beta cap with y, whatever y is, so whatever y is, substitute y. You know y, let me just write something here. And again, follow me here. Y, as we know it, this y alone is the whole of this. So what we did is that we substitute that y, which is x beta plus the epsilon, into it. And now that you've substituted, you can expand. You can pull out this x prime x to the power negative 1 x prime, okay, multiplying the x beta plus the same thing, x prime x to the power negative 1, okay, x prime, okay, multiplying the epsilon. Okay, so you can have that two part of this equation. And when you have the two part of the equation, you can manipulate it and do something. Watch. Okay. What you do is this. Oops. What you do is that, so this is the expansion that I just did. You will note that the expected, when you take the expected values, the expected value of this one, the expected value of beta is the beta cap. You did that before, previously. The expected value of beta is the beta cap. So when I take the expected value of everything, expected value of beta becomes this beta cap. But what about the expected value of the second part? What about? Well, we can see the error term is there. And the error term tells you that when you take the expected value of the error term, you get 0. So everything multiplying that part is also going to be 0. Therefore, the expected value of the beta cap is the beta. Now, how do you find the variance of the beta? You're going to substitute that, because remember, the variance is given by beta cap minus beta prime, and then beta cap minus beta without a prime. Now, this beta cap, we know it. That's it here. Okay. We know it, the beta cap. And then we know the beta. So we can substitute them. Okay. The beta cap is this whole thing. And then the beta is that. The beta cap is the same whole thing. And then the beta is this beta here. So we can substitute them into the original equation and then take their expected values. When you take their expected values, we can now conclude that the variance of the beta cap is the expected value of everything in here. Well, I've already told you that the expected value of this beta is the beta cap. The expected value of this beta is the beta cap. So we know that already. So what about the expected value of the one multiplying the errors? Well, without using the error term, keeping it as it is, you can now realize that you can expand what is in the bracket here. You can expand it. So x prime x to the power -1, it will have a prime, and then x prime x to the power -1 will not have a prime. Now watch it. We can, for those of you who don't know, when you have x prime with a prime, you get x. Keep this formula. Okay, x prime. That is when you change the row, and you change the row back to a prime, you get a column. Okay, so that is a transpose times a transpose. You can have that. Use that principle here. And so when we when we multiply this term by that term here, remember that the terms on the left here, they have primes. So it means that this x prime here will have x prime prime. This x prime here will have x prime prime. Okay, those without a prime will have. And then error term will also have a prime like that. Keep that in mind. And so we can conclude that our variance of beta is expected value of everything here. We have just expanded them. But what's something here? When you have this prime here, okay, and you actually multiply it by this, because this second part doesn't have a prime, it will cancel the one that has a prime. And so eventually, when some of them will cancel, you're going to have the middle one. The middle one here, which is the error term, will have epsilon prime epsilon. Epsilon prime epsilon. And when you arrange each one of these, remember that the part here has a prime, the part here doesn't have a prime. You are going to get this. You're going to get what is in the bracket here. And on the basis of this, you can take the expected value. You can expand and take this. You can pull out the expected value of all the elements here is the same thing because they are matrices. But then the one in the middle here is very significant. The one here. Okay. The expected value of this is a constant variance. The expected value, the epsilon prime epsilon, its expected value is the constant variance, the what we call the homogeneity, the variance homogeneity. As for the outer layers, the one here and the one here, you can cancel some of them using the base and then the exponent principle. And on the basis of that, you can see that, and when I say the expected value of the epsilon prime is a constant variance, that is it. The way we define a constant variance was this. Okay. And so having defined a constant variance, you can now work what is outside of it. And again, it's multiplication. And so we can say that this is a rearrangement. Watch this first part. The first part will cancel because one is to the power -1, one is to the power +1. They will go. And so our final variance will be sigma square and what was left in the end here. Called error demonstrator. That is how you prove that the variance, so the variance of beta cap, the variance is what is known as the variance covariance matrix. This is a power. You use the variance covariance matrix to solve all the other elements of the regression. What the software is doing is that the software is calculating this thing for you and solving it. So in general, these are the variances. The variances are in the right diagonals and the covariances are in the up diagonals. You use this, and without you noticing, the software is using this variance covariance formula to find your beta parameters for you. So we know that the variance, the mean is the beta cap. The expected value of beta is beta cap. We know that having found the variance now, the variance of beta cap, which we just did, okay, then we can now conclude that beta cap is normally distributed, okay, with this expected value and then with this variance. And I've already said that the diagonal elements are the variances, whilst the off diagonals are the covariances. You need this. Okay, somebody will ask, why all these Hebrew? What is the essence of all this to your life? Well, the variances will tell you about the variability or the spread in the data set, and you need to know it. The covariances will tell you the extent to which corresponding elements from the two sets are ordered. Okay. All of them help you to understand how the various tests, and you're going to see them, the tests, the t-statistics, all of these things are done. You're able to determine the p-values. You're able to determine whether a particular variable is significant or is not significant. This is what helps you to be able to get all of that. Okay. And you are able to determine all of this. Just that for some of you, you have never looked at it naturally. When you are calculating the standard errors of the estimators, you need this variance covariance matrix. In a logistic regression, you are creating a matrix for the estimated coefficient. Okay. You're creating a matrix for the estimated coefficient. You need this. It will help you to see the variances. Okay. So how do you interpret a coefficient? This variance covariance matrix is what helps you. How do you determine whether the model is significant? How do you determine the partial test, the joint significant test? The variance covariance matrix gives you all of that. That is why it is important to know all of this. All right, ladies and gentlemen, that brings us to the end of the mathematical ambience, the statistical ambience of the period. Now we are going to look at practical. Next time we meet, we are going to look at how to put all of this into a real life data set. But since you are advanced students, you got to know advanced things, okay, so that your life will be different from the life of those who don't know advanced things there. Okay. We'll come back to our data set that we have, the Brukutu venture data. We'll learn basically, I think I need to conclude quickly on dummy variables, okay, but because of time, I will not. Okay, we'll look briefly at dummy variables and then we'll apply all that we've done to the work that you have recognized.